Hey Calculus, welcome back. Our objective today is going to be to find volumes with known cross-sections. I've got the checklist on the screen. You know what to do from here. So I've got a picture on the screen of some 3D shapes that I've made, and these are the kinds of shapes that we are going to calculate the volumes of. You can see that these are quite a bit different from what we would look at in geometry class, because you'll notice that they are made up of all these same shapes, all these same cross-sections, but those cross-sections vary, right? Kind of depending on that area of the base that we have, okay? So here is one. Let's see if I can do this. So here's kind of a close-up one. We're going to start looking at how to calculate the volumes of these kinds of things. And hopefully you can see, I mean, this is not a perfect replica, obviously. A perfect replica would have an infinite number of these shapes. Can you tell what kind of shape I used for this model? These are all semicircles, right? And so I'm going to sum up an infinite number of semicircles for something like this. And if I want an infinite sum, what would I use? We'd use an integral, okay? So I want to integrate an infinite number of semicircles if I want to find the volume of this thing, okay? The thing is that my semicircles vary, right? The diameter varies based on, hopefully you can tell, this function that I have here, okay? So we're going to be looking at calculating the volumes of these kinds of shapes. But before we do that, we need to practice some geometry formulas because we're going to be summing up a whole bunch of different shapes. So first pause on your screen, can you please copy what I have, and then we'll fill in the formulas together. All right, so let's fill these in. Area of a circle with diameter d. Well, let's start with the radius. We know that the radius of a circle, the area of a circle with radius r is pi r squared, right? And we know that the radius is half the diameter, right? Diameter divided by 2. So if I plug this in, I get pi times d divided by 2 squared, okay? So if I square this whole thing, I get d squared over 4. So cleaning this up, my coefficient becomes pi over 4 d squared, right? Now, if you notice in that previous one, I didn't put circles on there, I put semicircles on my the base of my region, okay? So if I do semicircles, it would just be half of this, right? So half of pi over 4 times d squared is going to be pi over 8 d squared, right? Dividing by 2 is the same as multiplying by a half. All right, area of a square with side s is just side squared. A rectangle with length L and height h will be length times height, right? Sometimes you might see base and width, so base times width. However you see it, you want to make sure that it is in terms of only one side. And we'll do an example to make that a little bit more clear, okay? Isosceles right triangle with leg L. Well, if I have isosceles right, that would be something like this. These are both L. Can you tell that that is half a square, right? So this is going to be 1/2 leg squared, all right? Equilateral triangle with side S. You can take my word for it for now, but this is square root of 3 over 4 times your side squared, okay? So notice that these all pretty much have a square in them. I mean, the rectangle is maybe a little bit different, but typically once you get it in terms of just one of the sides, like either the base or the width, you're going to have a squared in this formula as well. So what you really want to commit to memory are these coefficients in front, like this pi over 8 for semicircles, and this 1/2 for isosceles right, square root of 3 over 4 for equilateral triangle, and then keep in mind that this is area, so we'll be squaring each of those pieces. All right, so let's try one together. And first pause on your screen. You don't need to copy all the words. Will you just copy the equations that I underlined, copy the graph for me, and then do make a note that we are going to put semicircles onto this region. So go ahead and copy those pieces and then hit continue when you're ready to work this together. All right, so we're going to do a 2D kind of representation of what's going on 3D here. So I've given you the base of the region. Hopefully you can see that here, that I started with y equals x squared, the positive x-axis, and going from x equals 0 to x equals 1. So that's kind of the region I've given you here. So let's go ahead. I'm going to force another pause on your screen. Can you go ahead and just lightly shade, either with pencil or highlighter, the region that we are looking at? All right, so I've done kind of rough shading here of the region that we are going to stick all these semicircles on, okay? So let's draw just one representative semicircle. So what I'm going to do is just pick one slice, and notice that it told us to go perpendicular to the x-axis. So I have to be, everything's going to be in terms of x here. So if I go perpendicular to the x-axis, I'm just going to draw kind of one slice for us. And this is going to represent one diameter, and it's going to kind of shoot out of your computer screen and wrap back around and come back. So here's my diameter, and then it's going to pop out of the screen and then sort of come back here, okay? So what I want to do is I want to sum up an infinite number of little diameters, right? So here, since everything's going to be in terms of x, take a look at your domain of the yellow section. So the yellow section goes from x equals 0 to x equals 1. I'm going to sum up a whole bunch of semicircles, and the formula for a semicircle, if you look at your notes, should be pi over 8 times diameter squared. So there's all those summed up, and then each little semicircle has a teeny tiny depth, right? And so I'm going to denote that with my dx. So take a look at how many dimensions here. You've got 2 here from squaring the diameter, and then another, that dx, that's 3 dimensions, which is what we need for volume, okay? All right, so I'm going to bring that pi over 8 out. I've still got integral from 0 to 1. Now all I need is a formula for my diameter. Well, I've drawn it here. Go top minus bottom. So this top function here was y equals x squared. This bottom function here is the positive x-axis, which is y equals 0. So when I go top minus bottom, I have x squared minus 0, and I know that doesn't affect it, but let's get in the habit of figuring out top and bottom. So that's my diameter. Don't forget just to square it, dx. All right, okay, let's put that in the calculator, see what we. All right, so I'm going to go alpha y equals enter to grab that fraction bar, and then pi over 8, and I'm going to go math 9, 0 to 1, and then I've got x, go ahead and open up a new set of parentheses, so x squared minus 0, again I know it doesn't affect it, but you're going to be grateful if you get into this habit of always looking for top and bottom, so x squared minus 0, quantity squared dx. All right, so I'm getting a pretty small number, which makes sense because look here, right, if I make this like square, 1 unit square, and then try to pop out of that, it's definitely going to be less than 1 cubic unit, okay? So I'm getting, if I truncate, I'm getting 0.078. All right, so that is that volume. Let's take a look at another model. So notice I've got kind of our parabola tilted here. That gray region is the region of our base. And so now let's stick some semicircles on here. And here's a nice model. So I just summed up all those semicircles, and they had a varying diameter, right? But each diameter followed this formula of the top curve minus the bottom curve, right? And so then we could do this integral and get our approximation that we got there. And this I can rotate and kind of see it from multiple angles here. Now do not freak out if you're like, I cannot picture these, that's totally fine. All we need to do is figure out what the region of our base is, like this one, and then figure out if we are going perpendicular to the x-axis or y-axis, and then grab that formula from geometry, because we're just going to sum up a whole bunch of whatever shapes they ask us to sum up, okay? All right. Force a pause on your screen. Can you please copy the graph that I have on the left? All right, so you always want to start with a graph of your region. We typically call it region R. And then what we want to do is draw one representative piece of whatever shape we're putting in. So in this case, we want to stick a whole bunch of rectangles on this shape, right? And the rectangles are going to have their base in R, the width is going to pop out of the screen, and the width is going to be twice the base, right? So if we have rectangles with base times width, and width is twice the base, then my formula for the area of a rectangle is going to be 2 base squared, okay? I just need to figure out how my bases are varying. So I'm going to come back to my region here. Let's pick out one base. You can put it anywhere in your region. Just make sure you're going perpendicular to the x-axis. That's what the directions told us. So this is going to be 1 base, okay? So I'm going to sum up an infinite number of bases, or do an integral, an elongated S. What is the domain of this gray shaded region R? The domain is 0 to 1, and I want to take a whole bunch of rectangles with teeny tiny width, or depth, right? All right, so let's bring that 2 out. Then I'm going to go integral from 0 to 1. Now I need a formula for B. Well, I can tell that's top minus bottom. So the top function, let's call it y1, and the bottom function, this cosine, let's call that y2. So I'm going to go y1 minus y2, and I still need to square that, dx. We can just put that in the calculator. So I'm going to show you all, I just went ahead and put my functions into y1 and y2, and then I can type it into the home screen exactly as is. So I'm going to go 2, math 9, 0 to 1, and then open up a new set of parentheses, and I'm going to go alpha trace to grab y1 minus alpha trace number 2, close parentheses, square, oh dear, and then dx, and we are getting 0.922. Okay, so this is all about just, I want to take that formula from geometry, I'm going to take an integral of that, because I'm going to sum up a whole bunch of like rectangles in this case, and then all we have left to do is figure out what the top function is minus the bottom function, because that's going to give us the length of the base, right? The base is going to vary dependent on what x value I'm on between 0 and 1, but it's always going to follow this formula of the top y value minus the bottom y value. First pause on your screen, can you just copy the equations as well as the graph, and then we will do this one together. Okay, we're back. So this is actually question 3 from your assignment. And I just want to first make sure that you really get a clear picture of what the region is that we've bounded. Okay, so first I see x equals y. That's got to be this line with a slant to it, right? That's got to be this piece. And then I've got x equals 1 over y squared. So that's got to be this curve, right? And then we've got y equals 2, which is this horizontal line through the y-axis at 2. Okay, good. Now I'm going to force pause on your screen. Go ahead and lightly shade that region that's bounded by all 3 graphs. All right, so here is the region we should have shaded. Notice that we want right isosceles triangular cross sections perpendicular to the y-axis, okay? So let's go ahead and draw a representative slice. And I need to go perpendicular to the y-axis, so this would represent like one of my legs. The other leg would pop out of the screen. The hypotenuse would kind of come back over, okay? So for isosceles right, consult your formula sheet there. It goes 1/2 legs squared, okay? So I want to sum up a whole bunch of these. Now, this time, will everything be in terms of x or y? It's going to be in terms of y, because I'm going perpendicular to the y-axis. So now would you give me the range or the domain of the yellow region to get your A and your B? You give me range, so that's going to go from y equals 1 to y equals 2. So I'm going to go ahead and factor out that 1/2. I've still got integral from 1 to 2. Now I just need a formula for L. Okay, so is L going to be top minus bottom or right minus left? L is going to be right minus left, which is the red function minus the orange function. So the red was x equals y, minus the orange is 1 over y squared. Keep in mind that's L, and what do I want to do with L? I got to square it, and then I've still got this tiny depth of dy, okay? So let me show you how to plug this in. Remember, your calculator doesn't really know the difference in the home screen, whether it's an X or a Y. Now, I wouldn't go ahead and do like these in Y1 because that could get a little bit confusing, but I'm going to go ahead and go alpha y equals enter and grab my 1/2, and then I'm going to go math 9. So A is 1, B is 2, open up another set of parentheses, and again, it's a dummy variable at this point. I'm just going to put x minus 1 over x squared. Close that set of parentheses, square this dx, because that's what I'm telling the calculator to use as the dummy variable. And I'm getting 0.619. Okay, all right, you all, that is what I have. So just make sure you do a few things. Make sure you shade your region that you're going to put all these shapes on. Make sure you decide whether you're in terms of X or Y, because that will determine whether A and B come from your domain or your range. And this is how you know, okay? It'll tell you perpendicular to the X or Y axis. And then just grab that formula from geometry and sum up an infinite number of those. In other words, integrate those. And all this is calculator active. On the AP exam, they are almost always calculator active or setup only, okay? So your assignment is all calculator active, so you can check your work, and I'll see you all next time.